This is page 3 in your class notes on section 8.1, and we'll be going over initial value problem. There are usually conditions in the problem that determine specific values for the arbitrary constants. Generally, it requires n conditions to determine values for all n arbitrary constants for an nth order differential. So that means that if you have a first order differential, so you have y prime, then you need to have one, one initial condition. So for a first order equation, the single constant can be determined by specifying the value of the unknown function y of x at an arbitrary x value x sub 0. If you are given y x sub 0 is equal to y sub 0, this is called an initial value, and the problem of solving a first order equation with an initial value condition is called a first order initial value problem. Geometrically, the initial condition of y of x sub 0 is equal to y sub 0 has the effect of isolating the integral curve that passes through a particular point x sub 0, y sub 0 from the complete family of integral curves. So here's our first example. So it says to find a solution for the initial value problem. So here you're given y prime minus 5x is equal to 4, and the initial value that's given is y of 0 is equal to negative 2. So since this is a first order differential, you only need to be given one initial value to solve the problem. So first thing is I'm going to isolate the y prime. So here's y prime, and then that's going to equal, so take your negative 5x and bring it over to the other side, so it's 5x plus 4. So now I'm going to take the integral of both sides, so you end up with y, so I'm just integrating it, is equal to integral of this, so it's 5x plus 4 dx. Okay, next I'm just going to integrate that using the basic rule of integration. So y is equal to 5x squared over 2 plus 4x, and then I have my constant plus c. Okay, so this is what we call as a general solution. And now I want these particular solution. So I use this initial value of y of 0 is equal to negative 2. And so it's y of 0 is equal to, now in all of my x's here, I'm going to put in 0. So it'll be 5 times 0 squared over 2 plus 4 times 0, and then plus c, and that is equal to a negative 2. So solve that. This drops out, this drops out. So then you get c is equal to a negative 2. So my particular solution is y equals 5x squared over 2 plus 4x minus 2. So here is my general. And then my particular, it's going to be this. So notice that the c value gets filled in. So you've got all these different possible equations or graphs that could come out of this. And here what you're saying is that it's got to go through this one particular point of 0, negative 2. So then the value for c has to be a negative 2. Okay, in my next example, I have a second order differential because this is a y double prime. So I have y double prime minus 2x plus 1 is equal to 0. And this time I'm given two conditions. Y of 0 is equal to 3 and y prime of 0 is equal to negative 5. So I'll first of all isolate the y double prime. So that is y double prime is equal to 2x minus 1. And then if I integrate that, that gives me y prime is equal to 2x minus 1 dx. So I take this integral and I get y prime is equal to x squared minus x plus, and I'm going to use c1 since we're going to have two different constants that we're going to deal with. So now I'm going to use my y prime, so it's this one here, this initial value. So y prime of 0 is equal to, this drops out, so you get c1 is equal to negative 5. So then you end up with a particular first order differential as y prime is equal to x squared minus x, and then you have a minus 5, right? So that comes from this where c1 gets filled in. And then I have to take the integral again. So you have y is equal to integral of x squared minus x minus 5 dx. Take this integral, so that's x cubed over 3 minus x squared over 2 minus 5x plus, and then I'll call this as a C2. Substituting in your values, now I'm using this condition. So you have y of 0 is equal to 3. So y of 0 is equal to 3, and this drops out, this drops out, this drops out because all of your x's are zeros. So you get C2 is equal to 3. So then my solution to the original function is going to be y equals x cubed minus 3 minus x squared over 2 minus 5x plus 3. Many physical and social problems in real life involve rates of change. Many of these problems can be modeled by differential equations. I'd like you to read through pages 563 to 565 for examples of the modeling process in your textbook. Okay, here's the fourth example. Suppose that a particle moves along an s-axis in such a way that its velocity v of t is always half of s of t. Find a differential equation whose solution is s of t. So I'm just going to interpret what they stated right here. It says that the velocity v of t is always half of s of t. So I have v of t is equal to 1/2 s of t. So in order to make it as a differential equation, I need to bring in the variable in terms of s. So that's going to be v of t is the same thing as ds dt, and then that's going to equal 1/2 s. For 4b, the question is, suppose that a particle moves along an s-axis in such a way that its acceleration a of t is always twice the velocity. Find the differential equation whose solution is s of t. Okay, so for this one, you're given that the acceleration a of t is 2 times the velocity. So I start off with a of t is equal to 2v of t. And then we know that a of t is the double derivative of s of t, so I can write it as s squared or d squared s over dt squared. And then the velocity is just the derivative of s, so it's ds dt. So then I substitute the a of t, which is this, so it's d squared s over dt squared. Right, so I put it back into this one here. And then in place of the v of t, I'm putting in ds dt. So this is a differential whose solution is in terms of s of t. Okay, that completes the notes for section 8.1, and now you should be able to do your homework.